This being said, it's a pleasure also to have Colin McLarty. For this time, is here only for 3 days. Perhaps next time we will stay here 2 months, 3 months. Why not? It will be a good idea. And his talk today is the role of proof in proof theory with focus on Fermat last theorem. I think that it was already here once. The idea we have 2 hours. If you want to speak 1 hour, then you speak 1 hour, 1 hour discussion. You want to speak more, we have less discussion. If you accept an interruption, there is interruption. So the idea is to have very formal and very friendly.
Yeah, if people want to talk about something, talk about it then too.
Okay.
Yeah, absolutely. Yeah, so this bridge, this is slightly older than Fermat's last theorem. Probably, we don't know when the conjecture was, well, when the marginal note was written. This is where Fermat was living. I'll start. I'm going to be talking a lot about Angus MacIntyre because he's the person who's done most on this. In a paper he wrote on proof theory, after the proof of Fermat's last theorem, but before he was thinking about that in particular, this is presented to the Royal Society, and he says, from the perspective of this paper, the mathematical significance of proof theory is that it provides methods which can, if used with discretion, reorganize informal proofs so they yield more information. The word informal is not important here. It could be a fully formalized proof that you might want to reorganize it in some way. So it's not in proof mining, reverse mathematics. I mean, this perspective is like lots of various perspectives that are going on. Now he also describes the beauty of the best proof theory. He obviously his heart is in model theory, but I'm going to urge a synergy between beauty and information. Even if proof theory only gave information that could be found other ways, it could still valuably systematize access to that information. Of course, it's necessary, in fact, that it only gives information that could be found other ways. There's always other ways to do anything. I want to talk about the importance of keeping those together, and I will insist there cannot be any mathematical or aesthetic benefit from simply believing that the proof of FLT is expressible in PA. It just does you no good to believe that if you don't have a verifiable understanding of how you would express the proof in PA. Not that it's important to get the whole thing written in PA, but if you don't have a verifiable understanding of how the key points would get there, it doesn't even no good to believe they could be. But Angus doubts the value of such a theory so long as some people know enough. Here we have a long quote. I think it just needs this. He describes unwinding, which is Georg Kreisel's term for how you study a proof this way. This is the activity of so this is Angus writing. This is the activity of taking an informal mathematical proof, giving an analysis of where it's proved, i.e. in what formal axiomatic system, doing some thought experiments on that proof to give sharper information on what's being proved, usually more than the original prover thought. The thought experiments involve varied means, which Kreisel compared to the means of applied mathematics, famously compared to applied mathematics. It is not easy and perhaps not even worthwhile to formalize, systematize them. It is, on the other hand, at least healthy for mathematics if some people know these techniques very well and look out for areas in which to apply them. Well, I want to focus on not easy and perhaps not worthwhile. Well, perhaps indeed. I mean, anything might turn out not to be worthwhile, perhaps. I'm going to compare Navier-Stokes. There's been huge theoretical progress lately in Navier-Stokes on solutions that really genuinely cannot physically exist. They depend, for a start, on perfect continuity of matter. No one believes that matter is actually continuous. And these things make no sense if there's any discreteness in matter. I just, since I mentioned beauty, I thought I'd give you the first of the Navier-Stokes equations. Don't worry, we're not going to go into it in detail, but it's beautiful, right? Just see it. It's nice to see. It's not easy. Theoretical progress on Navier-Stokes is not easy, and probably some applied experts think the pure theory is not worthwhile. I suppose there are tens of thousands of experts on applying Navier-Stokes. Navier-Stokes is widely applied all over the place in engineering and physics. But practical numerical approximations run into theoretical problems of instability and singularities. If you're not doing dead routine applications, no matter how practical your applications are, if they're not entirely routine, which many of them are because it's used so extensively, but anything beyond the most routine applications will run into theoretical difficulties too. The equation is just that difficult. So there's no conflict between pure theory and application in Navier-Stokes, and I kind of think there's not in proof theory either. The Clay Millennium Prize problem on Navier-Stokes is entirely theoretical. It took me a while to realize how strongly that prize description is skewed towards pure theory. This is not exactly, it's not a prejudice in favor of pure theory. It's a prejudice in favor of having questions that have clear-cut criteria for an answer. The Clay problems, they want to be able to say, you did solve it, you didn't solve it. They don't want it to be hard to tell whether what you did counts as a solution. That suggests stripping it down to its barest theoretical form. The theory is getting a lot of play on quanta. Now in 2011, McIntyre, he was speaking at the Horizons of Truth seminar on Gödel. And there's a beautiful volume came out of that. He, like a lot of model theorists, when there was this wave of meetings in honor of Gödel, and they would be asked to speak about Gödel's contributions to model theory, they would have to say, well, that's not really his strongest suit. Gödel wasn't really that important in model theory. Although I think what they misunderstand, or what they underestimate there is a lot of math. What they'll say is a lot of the current model theory depends on theories in which the Gödel phenomenon does not apply. The model theory of real closed fields, the model theory of O-minimal theories in general. Beautiful stuff, and it depends on Gödel's theorem not applying to those axioms. But precisely so, you have to know Gödel's theorem and make sure it doesn't apply to your axioms. It's not separate from Gödel's theorem. It's deliberately avoiding places where that will apply. As to Fermat's last theorem, Angus says, distinct regions of the Wiles proof are almost all hitherto unvisited by proof theorists. Some, but certainly not all this territory is known to some model theorists. There's no reason to list them all here. I have to say, I've had some conversations with people who will insist that Angus has shown that Fermat's last theorem is a theorem of PA. Well, Angus doesn't say so. He talks about what would remain to do to show that constantly. And yet some people have gotten the impression that he did show that. What Angus says is that it hasn't even been visited yet by proof theorists. But what's common to all these issues is crucial, and this is a philosophical interest. This is not just a technical issue for Fermat's last theorem. It's the issue of finitary versus infinitary statements.
But Colin, the proof of Wiles, does it prove that Fermat's last theorem is true in all the model of PA? Or not?
Well, no.
It also by completeness guarantee that there is a proof. But I don't know whether we can tell that the proof ensure that the last Fermat theorem is true in all the model of PA.
No, that's what we don't know. We do know that it's true in the models of PA definable in all the models of Zermelo-Frenkel. But whether it's true in all models, definable in, say, in non-standard models as Zermelo or Frankel, that's not that's not yet known. Yeah. There was a large and sometimes ill-tempered discussion of whether the proof needs to use Grothendieck universes. Now, those do not provably exist in Zermelo or Frankel. If it needed universes, then you couldn't do it in ZF. Nobody from the start thought you needed universes. Grothendieck and Dieudonné introduced universes as a convenience. Now, they knew enough to know that universes are not conservative over ZF, but they are for statements of arithmetic. No, not even for statements of arithmetic. Not even for universes are not even conservative for statements of arithmetic, but they also knew that for the proofs being given here, they were eliminable. Nobody thought these proofs, their overall structure depended on universes. They just thought it was a convenient way to do it. So there was an unreasonable argument over whether the proofs. Well, there were two arguments over whether the proofs used. One was, do they need universes? No, nobody ever thought the proofs needed universes. The other was, do the published proofs talk about universes? Here is something that I think you need to know. Published proofs of great results in mathematics today do not start from the ground up. They don't start from anywhere close to the ground up. Do any of the references Wiles makes in his proof go to works that use universes? Yep. You only have to look at his list of references. Yep. Now, did he need that? No, he didn't need it, but do they occur in the references he gives? Yep. They do. This should have been very easy and uncontroversial. What made it more piquant to me was, I go, so I'm looking at Wiles's proof to see, do his references use universes? And I mentioned in the preface, he mentions this turning point where he used a certain duality theorem, and he cites a book which happens to be by authors whose initials are A, so it's the first book in the bibliography, and it uses universes. It just, again, the authors of that book did not think they needed to, but they did. But that's all. None of that is serious research matter. What's the serious question is, can it be proved in PA? And I'm inclined to believe it is, but my point here is, you don't learn anything from believing it is. You would learn something from knowing how it is. So here's Angus. The reals, complex, quaternions, the p-adic numbers, the absolute Galois group of the rationals, Tate modules, are all completions of finite. These are used in the proof. There's no question they're used in the proof. They're used seriously in the proof. A substantial amount of their first order theories admits natural finite approximations that do not quantify over second order entities. Putting proofs of the modularity thesis. Now, the modularity thesis is the tough theorem that Wiles actually proves, which when you combine it with Ribot's theorem gave, as everybody knew it would, Fermat's last theorem. Modularity was the key point of Wiles's argument. Putting proofs of modularity into PA will involve finding finite approximations of modularity and all the other principles that go into its proofs. Specifically, on stating the modularity thesis in PA, he says, I concede that spelling out the finite approximations would be a lengthy enterprise and would be useful to have some meta-theorems to apply. Sure, it could be useful. I expect it would be useful. If I could prove one, I would do it right now. I mean, whether I'll spend 6 months doing one, I don't know. I will mention Grothendieck's opinion, which I think is exactly right. You can only tell how hard a problem is after it's solved. We don't know how hard it would be to give these, because as Angus says, it's pretty much unknown territory among proof theorists. And Grothendieck is right that in principle, you can never tell how hard a problem is till after you've solved it. And then, of course, it may change just with progress later on. What Angus does in the appendix in 2011, he says the original purpose of this appendix was to give good reasons for believing that the current proofs of Fermat's last theorem, it's worth knowing. I mean, has the proof been improved since Wiles? Yes. Dozens of steps of the proof have been improved since Wiles. None has been essentially changed. There's been terrific progress. Mark Kissing has made terrific progress on simplifying some parts, strengthening other parts, but it has not changed the fundamental character of the proof.
Being maybe easier, more than when you say improve.
Well, for one thing,
Parts of it.
the modularity thesis, as stated, is about complex curves. Kissing makes it for complex analytic manifolds of any dimension. Cool. It's not just for curves, it's in any dimension. I'm sure that many things that used to take 18 pages to prove now take 12. This is just not an improvement that anybody's going to get super worked up about.
Not in the sense of being turned to be more constructive.
Yeah.
Not in the sense of being more constructive.
No, not so far as I know.
Just shorter.
Yeah. Now, the problem with as criteria of constructability is that, of course, Fermat's last theorem is a statement about the non-existence of certain numbers. There's no use saying, well, can we get estimates? Because it says there aren't any. There's no estimates to be given to the numbers in an empty set. There are no solutions. So that criterion isn't useful here. In the proofs along the way, they're just too varied. I've looked at Rivet's proof. I've looked at modularity. I've looked at modularity largely through Angus's description of it. But there's an awful lot more there too. So his original purpose was to give good reasons to believe the current proofs of FLT can be modified without abandoning the grand lines of such proofs to proofs in PA. There's no possibility of giving a detailed account in a few pages. Understand there is also no current account in many pages. There just isn't one. It's not like he's got a longer one somewhere that he failed to cite here. He's correct, there was no chance of doing it in a few pages. But it doesn't mean he did it in a lot of pages either, yet. I hope, nevertheless, that the present account will convince all except professional skeptics that modularity thesis is really pi01, that it's actually, it's a statement of pound arithmetic whose only genuine unbounded quantifier is a universal in front of it.
One thing is to say that one other to think that you only need that. The statement that it could be pi01, but the proof it could not be.
Yeah. It's not. Yeah, stating it doesn't mean that the proof is that we know a proof of it there. In one way, the sharpest irony here is that the Gödel sentence is pi01. You can have independence in pi01. Angus quite correctly points out that nothing about this suggests that there will be Gödel incompleteness involved. But again, just having nothing suggested is not a proof. And he's not saying here that he is going to show, he's going to convince all except professional skeptics. This is not a phrase I've ever seen in another math paper. Nobody writes about convincing all but professional skeptics.
We should define professional skeptics. We should define professional skeptics.
Yeah. And I don't doubt this at all. If I thought that Fermat's last theorem might be independent of PA, I guess I'd be pursuing a demonstration, but I can't imagine very vividly because I don't think it at all. What I just think is we don't have a proof. But yeah, so he's and well, so that's what he's saying he's achieved. And I do like the achievement. I think it's a fine achievement when you understand what it is, and he says what it is. I have to say that I've talked with people who misunderstand the statement. He gives highly informed reasons. It's a beautiful survey. If you happen to be interested in the concrete issues of analyzing Wiles's proof from a logical point of view, you definitely want to read this appendix by Angus. If you want to familiarize yourself with the mathematical issues, I can mention two 700-page books. That's just a whole other world of problems. The beautiful club, Boston University, they had a colloquium about 2 years later You got 700 pages of contributions. What these contributions are meant to do, if you're a graduate student in number theory, you're familiar with basic modern techniques, you can read these 700 pages. You will now be prepared to read the references that Wiles uses in his proof. It won't supersede them, but you'll be prepared to go read them. It's just there's a massive amount in that proof. I was remembering the other day, and I'm remembering now, that BBC documentary where Wiles is talking about it. He comes to the crucial moment and he says he fixed that problem. The proof was now, and he starts to choke up a little and says, I'll never do anything like that again. I said, no, you won't. Most people will never do anything faintly like that in their lives. It's a wonderful moment, because I don't mean to make fun of him saying, no, you won't. It's like, wow, to have been there and say, well, I'll never do that again. I'm told that people who've been up in space spend the rest of their lives missing it, commonly. That's just But again, we learn nothing by believing these proofs would fit into PA until we see how they would fit into PA. I want to recall something that Dieudonné said about sectoral rigor. Jean Dieudonné has a very nice argument, which I think may be entirely true. I wouldn't call it a nice argument if I didn't think it might be quite true. That we have, contrary to people's opinion, we have not seen a steady rise of rigor in the history of mathematics. What we see is that number theory appears in the Greeks almost totally rigorous, and the Greek results of number theory have never been questioned since. Analysis takes rigorous form with, say, Weierstrass, and the standards of practical proof, what counts practically as a rigorous proof, have not changed since Weierstrass. In analysis, topology became rigorous with Brouwer and Hermann Weyl in the 1920s. It was not before that, and standards of rigor there have not changed since Brouwer and Hermann Weyl. We do not see a steady rise of rigor all over mathematics. What we see is that sections of mathematics achieve what becomes a universally recognized standard of rigor, and they keep that standard of rigor, and we're still happy with it today. The first serious proof theory is barely 100 years old. I'm thinking of people like Levenheim, the people before Gödel who proves, for example, the completeness theorem. When I teach Gödel's theorem at Case, I'll tell them this is the only serious 20th century theorem proved in any course on this campus. Because most of the serious 20th century theorems in mathematics have 19th century prerequisites and 18th century prerequisites. They have massive prerequisites, and we can't get you up to speed in one semester on them. Gödel's theorem has practically no prerequisites because it was brand new. You can teach Gödel's theorem from the ground up because it doesn't have a 200-year heritage. Conversely, we don't have very standardized norms of what counts as a rigorous argument in proof theory today, because it's a new thing. I think people I mean, there are people who are working on this, but Angus has questioned. I've said to Angus, have we proved this to the standards of proof theory? And he said, well, I don't know what the normal standards of proof theory are, and that's not a crazy thing to say. We don't have a standardization of proof theory yet. Maybe.
But it's not the Gödel theorem. It's not the Gödel theorem as such. It's the theory.
Yeah.
Is new. The Gödel theorem do not only has no all the proofs, yeah, also know all the statements.
Yeah. What I spent a lot of time trying to convince my students of this, because I guess I'm trying to absorb the wonder of it myself. For someone like Hilbert or Russell, say in 1910, they wondered, do the Peano axioms, are they complete? Do they prove everything? And they don't know what that would mean. They do not have a precise statement of what that would even mean. And I'm not faulting them, it's just wasn't there yet. And in Gödel's own proof, He proves it for Principia Mathematica and related systems. He was quite explicit. He didn't know what related systems, and he doesn't honestly mean Principia Mathematica. He means a substitute for it that he made up in the paper. Gödel, apparently, he was extremely impressed with Turing's paper on computability. He said, that's what I meant by related systems. I meant things whose axioms can be described in Turing's way. But this is 4 years after his paper. He doesn't know himself what the scope of his theorem is, legitimately doesn't, because the tools for describing it didn't exist yet. So I'm a little bit sympathetic to say, well, we don't really know what would count as proving this, but we certainly know that it could take more detail than it's got now. And here, the problem with expert reasons, well, I mean, everybody knows this. There's no real big news coming here. G.H. Hardy, no elementary proof of the prime number theorem is known. A proof of such a theorem, not fundamentally dependent on the theory of functions of a complex variable, seems to me extraordinarily unlikely. We have certain views about the logic of the theory. We think that some theorems are, as we say, lie deep, and others are nearer to the surface. He just has this sense. He has a sense common to all the leading number theorists of the world, which means his friends, of what's deep. And the prime number theorem is deep, and you're not going to prove it without using functions of a complex variable. But we know what happened. Facts quickly showed he was wrong about the prime number theorem. An elementary proof of the prime number theorem comes up just a few years after he said this. But more, Georg Kreisel proved that he was systematically wrong about depth in analytic number theory. He had a wholly mistaken criterion for depth. Hardy and others, they saw this calculation of complex variables and said that's deep. But what Kreisel realized was that over and over again, you could replace all that talk about complex variables with explicit rational estimates by finite Taylor series. Estimates of the log function or the log of 1 plus x or the log or the exponential function. It's really all, in terms of calculation, that's high school algebra. Now putting it together into the prime number theorem, that's not high school.
In a Taylor series, a Taylor polynomial. What you call a finite Taylor series is a Taylor polynomial, correct?
Yeah, it's just a polynomial. Yeah, and commonly you don't need the third term of it. Hardy was fundamentally mistaken about what's fundamentally at issue in depth in analytic number theory. And Hardy was an unexceptionable expert. You can't ask for a greater expert. Hardy was unexceptionably reflexive and considerate about what he's doing. He was just mistaken about depth in analysis because he didn't know the relevant logic, because nobody did yet. And then Kreisel comes up with that. Now, it doesn't automatically work. Kreisel didn't come up with a machine. You take proofs in analytic number theory and puff, you discover that they didn't need that. He came up with some theorems that apply generally. You have to do work to see if it works. And when you do that work, like with proofs in any part of mathematics, when you do the work, you normally get a stronger, more specific information than you had before. The work normally repays the effort. Kohlenbach's proof mining is about this. Kohlenbach has written some very nice stuff about this and done fantastic work in proof mining. As Angus says, it's about finding bounds and estimates over and over again. Wiles will make some statement about p-adic numbers. Everybody knows that he doesn't need the full statement about p-adic numbers because he only uses an approximation to it anyway. All he needed was a statement about some approximation, but it might be very hard to tell which approximation. Referring to the p-adic number lets him avoid saying which approximation he needs. Great idea. It's not a cheat. It's how you get math done instead of not getting it done. So what McIntyre or I would like to do is go through and say, here, when you see what he does with this, you can tell that he really only needed like the degree 3 Taylor polynomial. But it's not going to be, it's not going to be easy. Or more than that, he's going to say, we're going to say, here we have a degree n statement, but we can, this following conclusion only neglects the degree n plus 2 refinement of it. And there's going to be uniformity conditions here, where you need to know that how much the refinement, how high the refinement has to raise the degree does not change very fast with the degree. It may even go up with degree, but it doesn't go up very fast with degree. This is the kind of thing you need to show, and it's very detailed. As Angus said, it is not easy. But they can be extremely difficult. They can be impossible in principle, right? You know, if you sort the theorems of Pound arithmetic by length in their formal statement, for any one of them, there's a shortest proof because these are theorems. There's no undecidability question here. We were told these are theorems. So each theorem has a shortest proof. Now, among this length class, there's a longest shortest proof. So there's a well-defined function in Zermelo-Frankel set theory that takes lengths of sentences in PA and finds the length of the longest shortest proof of theorems with that length. What commonly will say, this function increases faster than any recursive function. The point here is it's not definable in PA. That cannot be definable in PA. Gödel's incompleteness theorem precludes it being definable in PA. It's a function, it's a bounding function, but you cannot define it with all the resources of Pound arithmetic. As a vast understatement, it cannot be a recursive function. It cannot be exceeded by any recursive function. Asymptotically exceeded. So bounds can be impossible in principle is a very interesting case to me of a currently hopeless bound. Gerrit Faltings won a Fields Medal for proving that a large class of Diophantine problems have at most finitely many integer solutions. Curves of genus more than one have at most finitely many rational points. Fantastic theorem. I have not followed that proof, but he got him a Fields Medal. There is no current hope of extracting an upper bound on how many a given problem has. This theorem has no constructive content. Now, for many individual problems, you can get a bound, but no, you're not going to get a bound out of Faltings' proof. And as a very pretty fact, Andrew Granville gave a short combinatory proof that Faltings' theorem implies there are just finitely many counterexamples to Fermat's last theorem for all exponents n together. It trivially implies that for any n, the degree n Fermat equation has at most finitely many solutions. But it non-trivially implies that there's at most finitely many solutions for all n put together. Now, if you could find an upper bound on that n, this would give a wholly different approach to proving Fermat's last theorem. You would prove that FLT is true from n on just by citing your modification of Faltings, and then you would just have to give individually up to n. But you know, we have individual proofs up to like n equals 37,000 or something.
Okay. What do you mean by just definitely?
Yeah.
Most definitely many. At most definitely many.
Yeah, at most finitely many. Yeah.
This is why I think that there are finitely many.
Yeah. Yeah. So making Faltings' theorem constructive or effective is the way they talk about it is effective. Can you, from Faltings' argument, find an upper bound to how many solutions a given curve, a given Diophantine problem has? No. I once asked Andrew whether there was any progress towards making that effective, and he was uncharacteristically stern in telling me I should not have asked. That was not a valuable question. Because he would love it if you could. And he is more aware than anyone else. You can't.
Sorry.
Yeah.
I think that I don't understand. One thing is to prove that there is enough finite upper bound.
Yeah.
Another thing is to identify
yeah.
upper bound.
Yeah.
So we could prove that there is a finite one, but not able to identify. So in this case, we cannot still prove finitely the theorem,
Yeah,
correct?
yeah.
So what your point here is to prove that there is a finite, that we cannot prove there is a finite one, or that.
Well, yeah, by combining
identify-
Granville's result using Faulting's result says that proves that there's some finite bound on how many counterexamples FLT can have. Now, we already know that bound is 0, but it's a different proof. But these proofs show there's some finite bound on how many exceptions there can be total for all degrees put together. But there's no hope of estimating that.
Okay, that's.
There's no hope of estimating that. And like I say, Andrew, I've had great conversations with Andrew, but he was very explicit. I should not have asked that question. It lowered his opinion. So when Angus says we just have to find, when Angus says we just have to find these for the modularity theorem, this may be an impossibly hard task. It is impossibly hard for some known problems. They're just not known to be involved in the proof of modularity. And now opening up to where this leads, understanding how Fermat's glass theorem is provable in PA would almost certainly show it's provable in some identifiable weak fragment of PA. It is a fact, any theorem of Peano arithmetic is already a theorem of an essentially weaker theory. Now, any infinitely axiomatized theorem, you can say, well, if you've got a proof of a theorem, you only use finitely many axioms, but the finitely many axioms might not be weaker than the whole theory was, but in PA they will be. In PA, that finite list will,
Well, what do you mean here by weaker?
proving consistency of. And that measure already suffices for the point I'm making here. Peano arithmetic has the fascinating property of being what's called reflexive. It actually does prove consistency of all its finite subtheories. This is, to me, very hard to come to grips with, but it's true. So that you have any proof of a theorem from PA, it only used finitely many axioms, take those as a finite subtheory, PA proves that's consistent and is stronger in that fairly crude sense. It proves consistency of that.
But perhaps it does not prove the joint consistency. Right?
No, well, not of all finite subtheories,
Yeah,
but
some finite pieces can be
Yeah.
consistent among themselves.
yeah,
But perhaps all together.
right. Well, it won't
Joint.
prove consistency of its whole self. Yeah, but it will prove consistency not only of any finitely axiomatized subtheory, of any subtheory with a finite bound on quantifier complexity of its axioms. It can prove consistency because you can give a truth definition. So it's provable in principle that if we show FLT as a theorem of PA, we have shown that it's a theorem of some weaker fragment of PA. But that doesn't mean we can tell what weaker fragment. But probably we will be able to tell. It's extremely unlikely that you could give this proof without being able to tell what weaker fragment it's a theorem of. Knowing it's a theorem of some weaker fragment gives us a better chance of proof theoretic benefits. It puts more limitations on the resources that were used and so authorizes stronger conclusions about, say, the growth rates of various functions that we consult, because this is sort of the paradigm is growth rates of functions. Angus is very certain Fermat's last theorem is provable in PA, but utterly agnostic about exponential function arithmetic. Exponential function arithmetic is, to put it roughly and I think comprehensively, you take a fragment of PA, cannot prove everything PA can. It cannot prove existence of any function that grows substantially faster than the exponential function. It's just, there's no maximum, but yeah, Harvey Friedman has famously conjectured that every arithmetic result proved in the annals of mathematics is provable in EFA, where there's this limitation. You can't prove anything faster growing than exponential exists. It's Friedman's, what he calls it, grand conjecture. I forget what. Well, Marco, what do you have?
I did not understand what is EFA.
EFA, well, technically, you take the Peano axiom, the finite part excluding induction, and now we're going to allow induction, but not for arbitrary formulas. We're only going to allow induction on formulas where all the quantifiers have some bound expressible in terms of exponential, iterated exponential, twice iterated exponential. But I'm saying those are not essentially faster going than exponential. You can only do induction if what that means is when you do induction, your induction condition can't involve looking very, very far out to tell what to do next. You can look out to the exponential of the functions you have numbers you have at hand to see if a thing happened yet. Or maybe to the squared the exponential of the exponential.
It's not a limitation of induction of the complexity of the formulas, it's limitation of induction on the bound.
In the bounded quantifiers.
In the bound to quantify.
Yeah.
The formula can be of any complexity, but the proof.
Yeah. This goes back to something Hilbert, when Hilbert was first concerned with finitary methods, he says, consider the claim that for every number, there's a prime number above it. He says, this is not really a finite statement because you don't know how far you might have to look for that prime. Now, in this case, it's not hard to say how far you might have to look for that prime. For any number, there's some number less than its exponential plus 1 that's prime. Now we've said how far you have to look, and that bound is based on exponential. Now, it happens that primes are easily shown to be at least that common. They are, in fact, much more common, but you're easily shown to be that common. It could have happened for some other property that you might have to look to prove this property of n. You might have to look at the exponential of the exponential of n. You might have to look that far out to verify this property. For finding an x prime, you only have to look out to its exponential plus 1. And you can put smaller bounds on that depending on how many theorems you're willing to use before. So Harvey is saying that in the mathematics that people actually use by his criterion of being published in the Annals of Mathematics, for those of you who actually know about this, the first 8 or 10 years of the Annals of Mathematics, it was kind of a recreational math magazine, and they talked about hyperexponential functions for recreation. So Harvey's grand conjecture is refuted in the first issues. It is irrelevantly refuted. It does not change the substance of the issue. But in fact, yes, they have they have tetration and but are there in the Annals of Math as a research journal, do any of the results in arithmetic use more than exponential growth rates? His grand conjecture is no, they don't. Angus has not offered to refute that conjecture yet. He's happy to say we don't know it. What Angus will say, we don't know it. Well, I think it's worth exploring. What I think, when you talk to mathematicians who know this proof, which is not every mathematician, but the ones who actually know this proof, they'll say, okay, well, sometimes what they'll say is, I don't know much about Peano arithmetic, but I think it can all be proved there. So, well, if you don't know much about Peano arithmetic, maybe your opinion is not, it's fine. I'm not saying you needed to. But I think what happens is when they're sitting in say a seminar and they're hearing a description of one of those steps, it's not just that they see this could be done by induction somehow. I think they have a feeling, I feel like that problem, I can see about how far I would have to look. I can sort of feel like there's a bound on how far I would look to verify that step. But their feelings, of course, don't become knowledge for me because I don't have the feelings. And so I think there is a serious reason why practitioners often feel like it's got to be provable in PA, which is they don't just think that these bounds can be proven somehow, they think they can be proven without looking very far. But that's a serious question. That's not something you can just have a feeling about. And Angus, I feel it's kind of arbitrary of him to say, well, PA, that's obvious. EFA, we don't know about. Because to me, all the current evidence that suggests to me that PA proves it equally suggests EFA does. It's inarticulate, it's vague, it's not strong, but I don't see where he drives any wedge between PA and EFA, and yet he draws very different conclusions about them.
What is the E of if FA, I suppose that is finite arithmetic.
Oh, EFA, exponential function arithmetic. It's sometimes elementary function arithmetic, but the more enlightening is exponential. Yeah. So when we're looking out to verify claims, we can look out to iterated exponential length. We can look at the exp of x. But what we can't do is what's called hyperexponential. We can't look, yeah.
Would EFA be strictly weaker than PRA? Or not?
What is the relation?
I believe it's stronger, but I'm not. No, maybe.
If PRA is the weaker one.
You can usually induct over all recursive.
Yeah, so it's got to be weaker. It's got to be, yes, because I think, here's another way to look at that. I believe the reverse mathematics hierarchy touches PRA. It does not touch EFA. EFA is below the radar of current reverse mathematics. And Harvey has noticed this and said, we need a more genuine reverse mathematics that will extend our radar, so to speak, down to EFA.
EFA is weaker
than PRA, yeah. Yeah, because this, I don't have something here, but this function, it takes 1 to 1, it takes 2 to 2 squared, it takes 3 to 3 to the 3 to the 3. It takes 4 to 4 to the 4 to the 4. This function is...
The reverse mathematical geometry, PRA corresponds to RCO, is that? RC.
I mean, but the point is that function is primitive recursive.
It's primitive recursive.
But it is not just exponential.
Yeah, it's not just, it's
hyper.
Yeah, it's hyper-exponential.
So PRA is.
Yeah, so PRA is stronger. And PRA is currently the lower bound to what reverse math can really hope to see.
Yeah.
And Harvey is aware of this, like I say, and has said, he's even given speculation how you might do a reverse math that can get down to EFA, because he's the author of this grand conjecture that all of existing math is EFA.
EFA is a first order theory.
Yes.
And
EFA is in fact a finitely axiomatized theory, although that proof is not simple.
The reverse mathematical geometry, a subsystem of second order.
Yeah. EFA is extremely weak, but what he's saying is that for practical problems, it's not weak. It's all we've ever wanted for practical problems. Go look in the annals of math, all the practical problems are solvable within EFA. I mean, Harvey knows a whole lot about things stronger than EFA, but he wants to say they're not what gets into the annals of math. They're not core mathematics. He likes to keep talking about core mathematics. Like I say, I don't see any grounds for Angus insisting on this split between we know it's PA, we can't even talk about whether it's EFA, but more than that, if he's right, we can't talk about whether it's PFA. He has said, we just have too little experience with EFA. And I say, raison de plus, let's go get some experience in the test case of Fermat's last theorem and see if it does give us EFA. As he said, these are whole areas untouched by proof theory. I want them to stop being untouched by proof theory. I have spent a year or two working hard on this, making so little progress that I don't normally mention the fact, but that's just me. So if he feels we have too little experience, let's go get the experience. Now, Angus is routinely involved in commissions to decide about science funding in the UK. I am not trying to make a decision about science funding in the UK. That's just a world that I don't know. But in terms of what I like to see this done, of course I'd like to see it done. I've tried to do some of it myself. What I have done everybody knew that the Grothendieck universes were eliminable. They're just a convenience. People said so from the start. It's just a convenience. But what I've shown is not only are they eliminable from the SGA, from Grothendieck's SGA, and from his major papers since then, the whole axiom scheme of replacement can be thrown away. The whole axiom scheme of unbounded separation can be thrown away. You can just take what's called finite order arithmetic. You just have numbers, sets of numbers, sets of numbers in the most naive second order plus third order plus fourth order arithmetic sense. And you can put the Grothendieck proofs as they are written into that set theory. It's not you can get the results of them. You can put the proofs as written. You just make things a little more explicit. Over and over again, where Grothendieck says, now consider such and so function, you have to take a moment to show this function will be contained in such and so Cartesian product. Take a moment to say that. Usually it's obvious. In fact, they commonly do say it. They just don't think it matters because they don't think it matters to avoid. So what I can show you is finite order arithmetic doesn't just suffice for Grothendieck's theorems, but for his proof methods. But that's remote from Peano arithmetic. That's completely remote from Peano arithmetic. But that I can actually show you. So this is where we have it, right? So up to now, I will mention Kevin Buzzard. Okay, Kevin Buzzard has a project to do a lean verification of some aspects of Fermat's last theorem. Some aspects. Well, there are aspects of Fermat's last theorem where there's no suspense whatever about whether they're PA. They are transparently PA, getting a formal verification. Great, now you got a formal. But whether it was PA, it was transparently PA. I hope he will look at some of the ones that were not transparently PA. But if he does, what's going to complicate the relation is that Koch itself, and so all of its descendants like Lean, have Grothendieck universes built in. They're not just stronger than PA, they're stronger than ZFC. They've got Grothendieck universes native. It's a standard type constructor. When Peter Schultz has this liquid tensor theorem, he shows what he considers a terrific theorem in analysis. It took him a year to write the proof. And he's very fun to listen to about this, but I'll still spoil the punchline for you. Go watch him anyway, because he's Peter Schultz. And he says it kept nagging at him, is this proof right? So he says, I called some of my friends who I knew were teaching it in their graduate seminars. And I said, well, how's it going? They said they're happy about it. They said, do your students understand the proof? And he said, oh, we're not doing the proof. Nobody understands the proof. So he thought, oh. So he contacts Kevin Buzzard's team and says, well, can we lean verify this proof? And they do. And it takes, I believe, 9 months, a team of roughly 6 people. It's a big effort. It's a wonderful effort. It's been beautifully described. But Peter Schultz in his proof eliminated Grothendieck universes in favor of a different concept that worked within Zermelo-Frankel. The lean verification scrapped that and went back to Grothendieck universes because they already had them resident in the language. So Buzzard's proof, whatever Buzzard does with FLT, you will have to look at the details to see, did it even use Grothendieck universes? Like I say, Schultz's proof of the liquid tensor theorem did use Grothendieck universes, the lean version of it, even though his published version used something weaker. So I'm very eager to see Buzzard's outcomes. Buzzard, as I recall, this is a 5-year grant, and it started about a year ago. So we're not waiting for the last news on it anytime soon. But there's how well it will bear on the question of a Peano arithmetic proof. Absolutely open question right now. Absolutely open question. So, okay, so that's what I have.
Thank you.
Yeah, and then Angus is too.
When you talked about rigor in mathematics, not necessarily increasing, but
In each
becoming-
subject, it gets established and
Yeah.
then stays.
How do you think that plays with like the current use of theorem provers and like, because that feels like a step up with.
Well, of course, when Dieudonné said that, he had no concept that theorem provers would ever exist. And we don't know what effect theorem provers will have. It's still reasonable to say that 0% of theorems have been computer verified. Thousands, probably everything in freshman calculus, but a lot of that was completely unsurprising. He wasn't thinking about that at all. But here's where I recommend. Okay, there's this 2-volume issue of the Bulletin of the American Mathematical Society on machine proof. And is it Andrew Komelin? I've forgotten Andrew Komelin. Johan Komelin. Yeah, okay, yeah, Johan Komelin has a fantastic article. He ran the programming team that did the lean verification of Peter Schultz's theorem. And he's got this fantastic article on how many issues there are in making sure that your verification is a verification of the theorem it was supposed to be. That this is not just a routine thing. So Dieudonné, one way he might be vindicated in the long run is that lean will get this terrific library for Greek level number theory. Later, they will get a terrific library for Weierstrass level analysis that lean will reproduce this because the programmers are having to take these steps that Komelin describes so well. The verification of Peter Schultz's liquid tensor theorem produces a lot of library entries on homological algebra, but these are not going to be the key steps of any future proof. They'll be the routine steps of future proofs. The key steps for the foreseeable future will require independent programming.
Yeah, so in this article that I'm happy that you cited it because I also found it very nice by Johan Komelin and Adam Topras. They make this case for spec-driven development, and they argue basically to use techniques from software engineering like refactoring to make a project like this viable. And Peter Schultz himself said, you know, my RAM is not enough to actually reliably check the proof that I myself came up with.
Yeah.
And so when they did this verification, I think they were saying at some point even they could only sort of see 2 or 3 lines ahead, but actually made them like able to not just actually prove that at the end of the day everything was correct, but they even improved the initially suggested theorem.
Yes.
So it's really, you know, 2 birds with 1 stone.
Yes. Yeah. Schultz has said, he's put it very pithily. He says, I think here we have a case where a proof assistant genuinely assisted with discovering the proof. I'm not sure I will do this with any future theorems. Because when we say proof assistant, this is shorthand for 9 months by a team of 6 people. And Peter has said, it's not clear that we couldn't have made as substantial improvements by working with each other that hard without the computer. And it's not meant to be because this is early days. So the optimist vision is as these libraries get built, it'll become really routine. The less optimistic version is no, it's going to stay hard. It may be valuable, but it's going to stay hard. Yeah.
Thanks.
I have a question about kind of universals. So when we compare universals from like ZFC, like, and no, it's a bit complicated because there's not one type theory out there, but like it's a whole slew of things, and they have kind of universals built within. But for a lot of them, it's not completely clear to me that they are one translation, even in strength to the ZFC analog. So I'm not.
Yeah. Well, and so I mean, Peter Schultz is a relevant example because he gives a genuinely weaker thing corresponding to the idea of universe, deliberately known to be. And already, what's his? Oh, I'm forgetting the name of the Bourbaki member. Back when Grothendieck and Dieudonné first proposed universals, one of the Bourbaki members said, well, instead of using inaccessible cardinals, well, why don't you just use limit cardinals? It won't justify as strong reasoning, but mere limit cardinals will probably work for most of your purposes. And they decided it required too much checking. Their goal was not to find a minimal solution. It was to find a solution where you didn't have to check things. So, but there's already weaker notions of universe have been proposed. And whether some of those are sneaking into the literature as universe, I don't know. I don't know how, I'm not in current touch with a lot of people in homotopy type theory, although Steve Audi and I go way back. I'm not sure how many people in homotopy type theory understand the difference between replacement and separation. Now, their models do require a replacement, and so their universes are equivalent to ZFC, but I'm not sure how many of them are aware that they required replacement or that that matters. And I'm not sure for what purposes they needed to require replacement. So yeah, in future, there will certainly be other notions of universe that are not equivalent. They already sort of exist.
I know that in Lane, like without any universes, it is strictly weaker than ZFC.
Oh, yes.
You need like 2 universes
Oh,
to get
yes.
up to ZFC, but because it has
Yeah,
comfortably many, it ends up being the same as.
because it doesn't have genuine replacement, but it does have separation inside universes. Yeah, separation in a universe is like replacement. But if you didn't have that ambient universe, separation would be much weaker than replacement. And I think people don't appreciate that issue. Often, many of the people in a field like that don't appreciate that issue.
Question. I want to make I go there because otherwise I think it makes the remark as a speaker. As nothing. So in my role of discussor, I will stay here. In my role of chair, I will go there. No, it seems to me that this makes an evidence a tension in the notion of rigor that we begin to have using artificial intelligence to prove systems. On one side, it seems to me that the notion of rigor should be connected with the idea that anything is proved within a certain context. So we do not prove Fermat like theorem. We prove Fermat like theorem starting from this assumption or rather the other here or there. And so it's true that generally mathematics we speak of one theorem as it were simply one theorem in totality of mathematics, but this is exactly what should be a no rigorous way of thinking. The Pythagorean theorem is a theorem of Euclidean geometry. It's not a theorem of mathematics. But on the other side, it seems to me that there is also this idea that to prove whether a theorem, to formalize and to be sure about a theorem is to put it in a proven system. And to put it in a proven system is considered not a way to show that the theorem is a theorem within the particular system that is englobed in the proven, but is true in mathematics in general. I don't know whether it's clear what I want to say. You have the impression that there is the idea that the need of formalization, that is a need of localization, when is on one side is a request of localization, and the other side is taken as a guarantee of global result. Because it can be proved in lean, so it's true.
And Kormelin's paper is a great cure for that. If it's proved in lean correctly.
No, one thing is to say that the proof is correct. One other thing is to say that this is a theorem on.
So there are some issues with respect to also like talk about certainty. Oh, now we put it in lean, we are certain. But in fact, there are all sorts of subtle issues that can arise also in these conversions. Some people call them translations, but in fact, that might not be the correct word. The problem is that sometimes you want to check the correctness of an informal argument, putting there, but when you convert it, maybe you change certain things, even like some essential things, so that you could have like a formal correct statement that doesn't correspond to the informal one. Or also sometimes formalizing definitions can be very tricky, and so you inadvertently prove something weaker by building some assumptions that you didn't build before in the definitions of the objects.
Yes, this is still another question.
It's another question.
It's another
a
point.
connected question, because like the way you phrase your question and many other people talk is like, now we formalize, we have the certainty. So I don't know, I mean, like, I think it's something.
But I think one answer to your question, I hope this is an answer to your question. I learned this from John Mayberry, who I admire very, very much. He's not with us anymore. And it's the strongest influence Aristotle's had on me, because Mayberry is a very strict Aristotelian. None of this avoids the problem of what do you believe. You saying that it follows from the ZFC axioms is a lovely fact, but it gets no real cutting force unless you say, and I believe the ZFC axioms. I think they're true. I think it's true that there are inaccessible cardinals. If you don't think it's true, your hypothetical result remains just a hypothetical.
The problem, Colin, is that I think that the word the truth should be eliminated from it.
But it can't.
That's my personal.
Yeah.
Because what does it mean?
But there's no end to relativization. Once you start relativizing, there's no end to saying what your assumptions were.
Would you say then that it is true that given ZFC and countable family of ordinals, then this, with that statement itself?
It's not matter. This is very mathematical. That's another story.
I
So
don't,
you say that the second proof work. It's true that the second proof work. Okay, that's another story.
but if you can formalize that, then by adding another universe, does it become mathematics again? The meta-mathematics?
I do not understand it.
If I can prove like with 7 ZFC universes that X is true, and then I say X is true, you have a problem with that.
But what does it mean that the F is true? You simply give a proof of the theorem.
Yeah.
Which is complete.
But then if I give a proof with
So
8
what is
universes,
true?
I can prove with 7 universes.
The fact that it is a bag is black is true. Okay, and in this exactly the same sense, in which it is true that the bag is black. It can be true that there is a certain proof of a certain statement within a certain formal system. This is an empirical fact. It's not an empirical fact.
Well,
I
because you could be wrong in believing there's a proof in that system.
Of course, there can also be that done, but that is another story. And believe that this is
And like all
black
things,
and it is not black, but that is another story. This is
well, I'm
black.
not sure it's another.
When I say this is black, it's true. I mean there are some facts that satisfy the fact.
Yeah.
And when I say within the system, I can prove this theorem, I am essentially in the same situation. There is certain fact that is proof theoretical fact that establish that starting from there, applying this rule, I arrive there. So there are two facts of the same sort. Another thing is to say that it's true that any vectorial space has a basis. That is another. This we do not use the verb true in the word true in the same way. So I have nothing against the use of the verb for true in the first sense.
Yeah.
The question is whether we should be allowed to use the word true in the second sense in mathematics, and I am very skeptical.
Well, but if you believe ZFC plus an inaccessible is true, then you do believe all the consequences. If you believe it's true, you don't have to keep saying if this, because you believe it's true. I don't have to keep saying, if I'm awake right now, I think I'm talking to Chapman. I do think I'm talking to Chapman. Now, you could say, well, if you're not dreaming, you're talking to Chapman, but I'm pretty sure I'm not dreaming, so don't say that.
This is a delicate question. The operator belief is a delicate question for the operator to know. The operator belief, I don't know. Do you accept that if I believe A and I believe A and they B, I believe B? is not so evident.
Well, and this is what I take from John Mayberry and his Aristotelianism. I know that many logical consequences of my beliefs are things I don't believe because I don't realize. But I do aspire to believe that logical consequences of my beliefs I also believe.
Yeah, but I think that the problem that Marco, maybe you can correct me if I'm understanding it. Okay. The problem is, what does it mean to be true? If we want to know whether or not the bag is black, we refer to the world and we examine the bag in the world, and then we see we have a way of knowing that this is true. But what methods allows us to know whether a mathematical statement is true? Do we have any way to look at certain objects somewhere and look and compare and say, yes, now we know that this mathematical statement is true. So maybe a mathematical statement, the only mathematical statement that can be verified to be true are mathematical statements of the form if then.
But they're not more believable than the conclusions.
No, but so you don't have to believe anything, because the thing is that you can check that are true if so it's all this, I guess, that all the statement that Michael wanted to say, that we can make sure that we can check that are true are the statement that says if thermal Frankel, then every vector space has a basis.
I am even more radical than that, but it's essentially what I want to say.
I don't understand, I guess, why if-then statements get to stay. Because if I say, a lot of times if you want to prove something, that PA proves something, you're not going to sit down and write the PA proof. You're going to prove in ZFC that PA proves something. So a lot of times saying PA proves, I don't know, some statement that's true in PA, what I really mean is ZFC proves. And then, of course, if I want to use ZFC, what do I mean? ZFC plus the universe.
In fact, I say, if you exhibit them, so of course there are proof that there are proof within a certain theorem, and of course this sort of truth or use of the word truth is exactly one use that I would eliminate. Okay, so when I say 2 plus 2 equals 4, and I prove it and I exhibit the proof, it's true that I proved that 2 plus 2 equals 4. But this is an empirical fact.
Nobody believes that.
The same sense in which the bag is true. But the sense of truth is not the same in which I say that 2 plus 2 equals 4 is true.
Yep. Well, I mean, Aristotle says you cannot argue with people who will affirm contradictions.
Sorry?
Aristotle says you cannot argue with people who will affirm contradictions. And he says you cannot teach ethics to men who are not well brought up. Aristotle tells you there's a baseline. If people don't have a certain baseline with you, you cannot expect to agree with them. And what I'm going to say is, yeah, ZFC, I am so sure it's true that I don't make it an antecedent any more than I make today's state an antecedent to every statement that I make, because I think today's state is not in question.
But what I wanted to say before the question of truth is that in some sense you began with a fantastic quotation by McIntyre that say that proof theory, I don't remember exactly what the content is, that proof theory allows us to increase our understanding. It does not increase our knowledge, but increase our knowledge of how it is. I don't remember what it is, right?
Well, what he says is actually a little trickier than that, because the truth is he doesn't think proof theory does teach us very much.
No, the next one. But perhaps what the first one.
The very first.
The very first. The first one. from the research this paper,
Yeah.
that's similar proof theories that provide method which can, if used with discretion, recognize informant so that they have more information. So when we rephrase an informal theory, or even a formal theory, I totally agree with you. When we recast in my language a formal theory or a theory, formal or informal, in another context, we gain information about what depends on what.
Well, but here, no, that's not what, he's not saying he'll get more information about the conclusion. We get more information about, say, estimates that would, that conclusion would involve.
Yes,
We don't become more certain of the conclusion.
On what depends on what.
Yeah,
Okay? So we have the theorem. But I make a very simple example. I prove, this is the example that we had in the APAP meeting when there was a discussion about the transition. We prove Pythagoras theorem using similarity of triangle. Okay? And then we go to first book of Euclid element, and we show that we can prove the same theorem in a much weaker system. So of course we have not proven the theorem, but we have shown that this theorem depends on something rather than something.
but that's not the kind of gain he's talking about here.
No,
He's talking about the gain, instead of saying for every number there's a greater prime, we say, oh, for every number there's a greater prime that's less than that number's exponential plus, or factorial plus one.
It's a strong.
Yeah, it's not that we change our faith that there's a greater prime, but we get an estimate of that prime. And in that sense, we keep our reasoning finite. Yeah, what we're getting out of this analysis is estimates of the various numbers.
I'm not sure to understand exactly.
Yeah.
I need my translator.
Maybe what you need is a statement that where that fails. Some statement about Ackermann function or something crazy
Yeah.
like that. Right? That you can't do in EFT, but you can do in PRA. Maybe that's the sort of thing you need.
But this is exactly what I'm saying.
Yeah.
Myself. My point is that to prove when you recast a theorem or a proof of a theorem within another context, you identify different
I think you had to make somebody talk.
dependent
Maybe I've
connection.
it's moving pretty fast.
And what I want to say, that this is not just a way to increase our understanding. This is what mathematics is. Mathematics is established what depends on what. It's not just established that.
You know, I honestly don't think 2 + 2 = 4 depends on anything. I just think it's true. You can prove it in many different systems, but I think it's true. I believed it was true long before I heard of any of those systems.
Yeah, because the danger here, Marco, is that they'll become turtles all the way down if you're not careful.
Sorry?
It'll become turtles all the way down if you're not careful. So if everything is simply saying what depends on what, what's the foundation of that? At some point you have to say, these are just, no, 2 + 2 = 4. I'm not worried about that anymore. And for Colin, ZFC is pretty foundational, right?
Yeah. I'm not interested in.
That is not sure. I don't remember now the number. I was assisting a talk by Jean-Paul van Bentegard, in which the statement is that the proof of 1 + 2 = 3 in Prima Mathematica. I do not remember.
Oh yeah, it's
many
pages and pages.
thousands of pages.
Yes.
So to say that it follows from it is actually that 1 + 2 = 3 is absolutely not clear. Absolutely not clear.
Yeah.
Well,
So-
you can't talk about proof without saying from what. And if I'm going to say one of the things I accept in any proof is everything that I learned by third grade, then 1 + 2 = 3 is axiomatic. I had certainly learned that by third grade.
And the bomb. I go.
Totally different question, just who was the audience for this paper?
Oh, which page? Of the one that he wrote in.
Proceedings of the Royal Society.
Okay, this is for the Royal Society. He's going and he's talking to all the leading scientists of England, all who also share responsibility for awarding funding, and telling them what he believes about proof theory, which I should mention that what he goes on to is to say, well, it doesn't do this very much. We don't actually get much from it. And I will tell you that there are proof theorists who are very unhappy that was.
So the paper is, the intention of the paper is to explain what proof theory does and does not do.
Yeah, to non-mathematicians. Yeah, to the smartest non-mathematicians in the world. I'm citing their self-image.
This kind of proof theory, though, is a specific kind, it's a specific tradition in proof theory, which is this complexity, using proof theory as a measure of complexities.
Yeah.
I mean, that's not quite fair.
Yeah.
That's essentially what that's about. But there's all this there's another tradition in proof theory of what's sometimes called structural proof theory.
Yes.
You know, concerns about display logic, things like that. And that has real engineering applications. It's made its way into computer science in pretty fundamental ways. So yes, he's right, but only if you sort of prescribe that proof theory is a certain kind of proof theory.
Well, in a way, this is the how far do the turtles go thing. He's saying from the perspective of this paper, he's not claiming to discuss all of it.
Yeah.
This is just what he's discussing. Now, what is he not discussing? I don't know. The Royal Society doesn't know.
And by the way, how do I get a job as a professional skeptic?
Yeah.
I think I missed my opportunity.
I don't know if you can.
What is that professional?
I don't know, and he's.
You are one.
It
sounds like it doesn't.
I have yet to get a check.
But you need to have a patent to be professional, or you can have a license.
You have
So you cannot pass an exam because then it would be skeptical about the exam.
Skeptical about this.
Okay.
I don't believe that any exam.
Exactly. And overall, you are skeptical about the proving you just fail. Any proof. Any proof is not good. I have a solution to the problem. Okay.
So you're saying that once rigor is established at a certain adequate level, whatever exactly that means in the field, it just stays there,
Yeah.
plateaus. And I'm wondering, considering Weierstrass, I mean, that seems to the first time it was really made, the calculus made rigorous, I think, was Weierstrass. For every epsilon, there is a delta.
Vast amounts of it explicitly in those terms, yes.
Yeah. Which seems like a use of quantifiers before they were supposed to have been invented by Peirce and Frege, by the way. Is using the delta and epsilon are variables.
Yes, and distinguishing continuity from uniform continuity, which is entirely about quantifier. Yeah.
However, when Peirce and Frege did systematize quantifiers, do you think that maybe indirectly made Weierstrass's rigorization more rigorous?
Well, something that I guess I feel is underexplored, and maybe Dries will go further with it. How far was, say, Hilbert influenced by, say Boole and any of these people? I just don't really know.
I don't understand your point because the use of quantifier, you look at Euclid use of quantifier, for example, when they prove of the existence of the fact that there are infinity prime number, there is use of quantifier, and the use of quantifier in this sense is equal to sort of mathematics. Okay, one thing is to say that. One other thing is to identify the difference between for A exists and exist for A. There are different things, and another thing is again is to write a formal language in which you manage the quantifier. So when we say that Frege invented the quantifier, we do not mean that Frege is the first one that explains the
Right.
Because for A, if you don't know what it means for any, you cannot really use it. And what do we mean is that really is the first one of the first one that codify
Right.
which to be used for quantify within a system.
As an independent operator.
Yeah. And I don't know who read that far into Frege at all, and I don't know what influence it had on any of those people.
I'm pretty sure that Russell
Mm-hmm.
didn't credit Peirce at all.
Mm-hmm.
He credited Frege, but not Peirce.
Well, at times he insults Frege in favor of Peano.
Yeah,
Sorry?
but he ignored the American.
Yeah.
He insulted a European, that's fine, but he ignored the American. Yeah, exactly.
Question? I am very worried because Walter is not asking questions.
I did.
He did.
During the talk, during the talk, so I would like to, I don't know. Are you sure you are what?
Well, like I say, study of proof have changed a lot. Right?
But
then-
then not the problem.
And then we have to agree with Thomas Kuhn that mathematics is a social subject that, I mean, truth is more social than metaphysics in a certain sense.
No, I don't.
Mathematics.
So repeat,
If you agree with Thomas Kuhn,
I do not agree.
if you don't agree, we should be aware truth in mathematics is more social than metaphysical.
But it is shockingly stable in fact compared to similarly sophisticated ideas.
You know, the rigor different of proof, the rigor of proofs have changed a lot. What is a proof in one period maybe is not accepted as a good proof in another period. You know more than me.
I think that's a ratchet, though. I don't think it goes in the opposite direction.
I think that there was nothing that was considered not a rigorous proof that later on was considered a rigorous proof.
I don't think so.
Maybe the infinitesimal thing, right? So proofs with infinitesimals and
That's an interesting.
Now, Roy Wagner, I'm not sure how he wants to pronounce this, just talked with him a little while ago, and what he'll really insist, this appearance that mathematics is cumulative is because we make it so, we insist on recasting the past so that we still believe what they believed. And I can't prove he's wrong about that. I'm not super sympathetic, but I'm bringing up his view here.
Yeah.
I always been skeptical about this idea, but
So you should.
there is the standard rigor is historically determined, but I've never been able to make it clear what is wrong in it. But I think that there is I think that what does it mean then? Starting from some claim and applying some deductive rule, you get other claims. This is rigor for Euclid and for us in exactly the same way. What is not clear is whether this deduction only use explicit rules or take for granted something without making it explicit.
Yeah.
So in this sense, the standard of rigor change, the sense that we consider that something cannot be taken for granted, that we considered before that we could have taken for granted. And so there were part of the deductive mechanism, even without being explicitated. But this is another story.
Follow the rules is always follow the rules, but the starting points are different.
Starting points are different. Of course, starting points are different. But the choice of starting point is not the person reading.
But also the ending points. I mean, is there anything Is there any geometric statement in Euclid's Elements that we don't currently believe as part of Euclidean geometry? Is there any statement in Diophantus that we don't believe is arithmetically true?
No, but in analysis, that we read, right?
Well, not
Or
from them, but from later, yeah. Yeah, yeah.
You're not in Euclidean numbers.
But are there statements in Weierstrass that we think, well, he just got it wrong? He just, that's less obvious. And I love that reference to Brouwer in Rigorization of Topology, because Brouwer's pre-intuitionistic papers on topology are astonishing. It's a terrible loss to me that he went into intuitionism, because his pre-intuitionist papers are fantastic. And you can read them today, and you can buy a textbook like Vick's Homology that's modeled on his arguments, and it's a graduate textbook today. So there was nobody models their treatment of topology on Riemann, let alone Poincaré. They're inspired by them, but they don't model it on how they did it. They model it on how Brouwer did it before he went into.
For his conversion.
Yeah, yeah.
Okay, even so on the question of Euclid geometry, we could tell a lot of things, because when we say that now we are rigorously established the first book of Euclid element, correct, what we mean is that we reconstruct the book of Euclid element within Hilbert.
Yeah, there's a question on the.
I did not know that. Okay, I came, Oliver. But our work with Euclid shows that when you want to stay closer to Euclid elements, for example, you avoid infinite line, that's not so evident what follows from what. Oliver, please go.
Yes, so it strikes me.
1 moment.
Yeah, you have stuff, sure.
How should we make 1 moment, Oliver? Can you speak?
I can speak.
So I think you can hear him on the speaker, but we have to turn off the room speaker.
So what should we do?
Why don't I just write the question in the chat so you guys don't waste time with this?
There's no computer here.
No, this is maximum already made.
No. So let's take computer.
What about this?
I should get.
Marco, isn't this a waste of your time? I can write it in the chat.
Yeah. Keep going.
I mean, we can try.
No.
While they're working that out, write it in the chat.
Okay, we'll do.
Go!
Now we hear you.
Go, Oliver. Now we hear you.
Okay, I'm sorry to be one of those Zoom people that slows down the event. It seems to me that 2 things are true. On the one hand, standards of rigor change up to a certain point. And as I think Colin said, something like this, that what we do is try and form a massive sort of encyclopedia of old results. And we try to restate them in such a way that it doesn't matter exactly which definitions or exactly which axioms the results were originally proved from. But at the same time, this much more abstract way of sort of recording our results, often there is an intuitive intended interpretation, such as arithmetic and geometry going all the way back to Euclid. And that is sort of the truths we prove about that are objective in a deeper sense, right? So there's 2 sources of stability. One is our grasp of the intuitive interpretation, and the other is the collective standards of rigor that we then use to go back and record results in such a way that they don't seem to depend on one mathematician's favorite definition versus another's.
Reaction? Is a question? Is this a question? What's your question, Oliver?
Do you think what I said was completely confused or only slightly?
Is there a third option?
Well, to me, one of the spooky things about Euclid's geometry, we say, well, we still believe it's true of Euclidean geometry, but what's Euclidean geometry? We don't believe it's true of space-time at all. Well, what is the Euclidean plane that we supposedly all knew all along? We don't believe they're Euclidean planes. So how do we get any claim that his axioms are correctly describing a thing that we don't think there is? And yet I feel that way. I mean, I do feel that way about him.
It was taught in English high schools until the late 70s or something like that. The textbooks were basically just Euclid, right? This kind of stability you don't find anywhere apart from maybe ethics. It just doesn't come up anywhere else. And that has to be explained. It's not enough just to say, well, you know, standards of rigor change and our formal systems change. That's not what's going on. There's a pattern there that we have always grasped.
And I think Poincaré may have the best explanation of that, which is that although Euclidean geometry for Poincaré, it's very clear Euclidean geometry isn't true. It was a convention we picked whether it should be true or not. But Euclidean geometry is radically simpler than any of the alternatives. That's an objective fact. And I agree with him. It's in a way that I don't know if I would want to describe it precisely. But yes, Euclidean geometry is radically simpler than, say, Riemannian or Lobachevskian. The way zero is simpler than any non-zero number, Euclidean geometry is simpler than the other axiomatic geometries. It's appalling when you actually try to prove things in the other axiomatic geometries. So there's a very intellectual problem. I'm not saying it's true.
Why is simpler? Because of similarity. What make it? I do not disagree. The entire thing is what make it simpler.
Well, because defects are zero instead of not being zero, and defects are awful hard to keep track of if they're not zero. They depend on the size of your drawing. I mean, so if your geometry depends on the size of your drawing, that's a much tougher world than where it doesn't depend.
Okay, so because it made change of scale, this is the reason that made it simpler. I argued for this in 40 years ago, exactly.
I'm not sure about zero though, being the simplest number.
Well, zero defect is easier to live with.
Oh, okay. I'm talking about just zero as a number. I was like, once maybe so, but I understand now.
Okay.
So, but when you say that the axiom of Euclid geometry do not describe
Physical space-time.
Complete space, what you are saying is that when you say that Pythagorean theorem is true, we use true in a different way than when we say that this is black. This is exactly my point.
Well, except that I'm kind of like Poincaré's answer. We didn't mean physical space-time. That's true because we don't believe those X. We did mean the intellectually simplest geometry.
Are you saying that the ZFC is the intellectually simplest foundation?
Well, no. People should remember. I like elementary theory of the category of sets. I do think it's not because I doubt anything in ZFC, but in terms of simplest foundation, I don't.
Well, but if simplicity is the criteria, that what you just mentioned should be true in ZFC.
Well, yeah, except at ZFC, by the time we're talking ZFC, we're confronting a huge body of mathematics, including all of Weierstrassian analysis, all of differential geometry. It's just incomparably different in scale than Euclid's axioms.
You mentioned the modularity theories at some point, of course.
Yeah.
There's no translation of the modularity theories into piano arithmetic. So the proof that we seek in piano arithmetic would not be a translation of the proof passing through the modularity theories. So all the people you mentioned interested in how many times the structure of the proof is the partly form. At some point you could have some portions where the part of the proof is directly translated, and the structure of the proof is respected. Like we have a proof of B from A is translated into the translation of B proof from the translation of A. And so there is some kind of linear translation, some kind of linear reflection. But at some points, of course, that would not work because, for instance, the modality thesis will not be some point.
Yeah. If we take modularity the way we normally would as a statement about complex numbers, you can't interpret complex numbers in PA.
Yeah.
But you can interpret all the rational estimates that go into the modularity thesis in PA. And if you can prove all the rational estimates, the rest is just taking completions. And I just want to say, okay, great, that's a real process, but it doesn't change the structure of the proof.
Okay.
Because the proof only used the approximations. Now, there are proofs that use the limit of it. Those ones aren't in PA. But he's saying, no, the use of modularity in Wiles doesn't use the limit. It only uses the approximations.
Okay.
And that's sort of obviously true. The question is, can these approximations be uniformly and systematically expressed in PA in a way that we can use? And that's depending on what approximations they really were and how they were really used, which I think it's fair to say, Angus, I mean, we talk about this, but neither of us really, we'd like to know a lot more about that.
And what do you call exactly approximation? Is the replacement of a rational number for a real number? What is approximation?
Well, I mean, when you define the real numbers as the Dedekind completion of rationals, your approximations are rational estimates.
Oh, okay.
And
So for you, approximation is replacement of a rational for a real.
Well, it's not just replacing a real by one rational, it's replacing a real by a chain of beliefs about rationals, where for some applications, you could stop the chain here.
You take the sum of these.
Yeah. And for many approximations, you don't do, I mean, you know, the prime number counting function, you know, it's an integer valued function. If you can approximate it to within 1/4, you know its exact value because there's only one integer in that range.
Yeah. Oh, I understand.
Yeah.
Other questions? Okay, so I think that we can thank Colin. Thank you very much. Now to drink beer and to have dinner. I wanted to tell you one thing. I began this section by welcoming Brice, and I do it again, welcome Brice, but I did not do something because I wanted to do it then. I want to ask Sylvia that tomorrow we leave. So Brice arrives and Sylvia leave. That's life. But it was also a very important presence for us, very beneficial and very insightful. And I hope that she will be back quickly. So, and also Jean-Jacques is for a short period this year, only for weeks. Okay. So I could not welcome Jean-Jacques because I already made it yesterday. But and he will not start so soon, so it's still not the time to send him au revoir. But thank you, Phil.
Thank you.
And Mark, I want to thank you and everybody else. It's not by accident I said, if I'm dreaming, I'm giving it some. Yeah, I don't believe I'm dreaming, but if I was dreaming, I might dream this.
Okay.
It is not too